back to our material, back to the oscillations. All right, so in the previous class, we finished discussing oscillations without damping, right? Which are not exposed to any damping forces, right? And then at the end of we looked at the example, oscillations of a bottle in a large bucket of water. And then we decided, okay, so next step to increase complexity, in order to increase complexity of the problem, so we added a damping force, right? And we assumed that the damping force is proportional to the speed of an object, our object, oscillating object, right? So basically, by doing this, we assume that the speed of the object is not large. Because if a speed of an object is large, then of course it's better to model the damping force using an expression which is proportional to the second power of the velocity, right? So we assume that here velocities are small, and as a result, our damping force is proportional to the speed of the object, right? And of course, points all the time opposite to the direction of motion, right? So we created this quickly system, right? So again, every time I assume everything is positive, right? So acceleration in the positive direction, right? Velocity, and as a result, our force is opposite, right? So then we applied Newton's second law, right? Because that's the foundation law which is capable of describing motion of any classical mechanical system, right? Doesn't matter which one, in our case, this oscillating. And so mx double dot equals minus b. B is the sort of constant connecting damping force with the velocity, right? Minus bx dot and minus kx. Again, force constant is k. Again, all these are applicable for more general situation, not just for a mass spring system. It's just in order to have something. I usually draw that a mass spring system, but of course it has a general validity, all this stuff. Right, so as a result, we divided by mass, and we ended up with this differential equation, second order. And then, of course, who wants to drag these constants, b over m, k over m? Of course, it makes sense to introduce new constants. Instead of b over m, we introduce 2 times beta, where beta is the damping constant. Basically, it characterizes the strength of a damping force, right? Beta characterizes the strength of the damping force. Factor of 2, in a few minutes, it will be obvious why this factor of 2 was chosen, right? And then instead of k over m, now we are going to add subscript 0, omega naught squared, right? And we're going to call it a natural frequency of the system, right? Because from now on we're going to have a few omegas. So now we have to be careful with these omegas, right? So there will be omega now naught, there will be then omega 1, then omega 2, there will be just omega, there will be plenty of omegas. So now we have to be careful. This omega sub 0, natural frequency, basically it's a frequency of the system if it doesn't have any damping, if it's not exposed to any damping forces, right? So natural frequency. Okay, so now let me rewrite this differential equation and start solving it. No, before we characterize it. Before doing that, we will characterize it. Okay, so let me rewrite it with constants. Basically, that's where we stopped in the previous class, right? Right. Okay, so let's call it names. First of all, second order again. Then, still linear. Why linear? Because if you have 2 solutions, if you construct linear combination of them, that will be also a solution of this equation. So it's a linear equation. Then, still homogeneous, because we don't have free terms. Each term has an X agent, right? KGB agent, right? So here X agent next to omega, X agent X dot, and again X double dot, right? So X agents are everywhere, X's are everywhere. So no free terms, so it's still homogeneous. Okay, let me write. It's still linear, homogeneous, differential equation, second order. Okay, I skipped second order. Differential equation, and still with constant coefficients, because this constant, 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 all these are constants with constant coefficients. Right. Okay, and now we need to solve it in order to see the response of the system, how the system is going to oscillate. Okay, so again, you can search for a solution in any form, right? But we're going to search for a solution in the exponential form because that's the best function. Right? Nothing can behaves better than exponential. No, behaves in terms of usage, right? So it's much easier to use exponential functions. So okay, x. Let me write. Let's search for a solution. Search for a solution in the form. Sorry. X equals e to the power of lambda t. Right. So plug it. Of course, we will get characteristic equation. Right. So it will be lambda squared e to the power of lambda t. I will remove immediately. Right. Then here, damn it, I should have framed this equation because now my eyes all the time over here. Okay, now let me put my finger here. All right, so 2 beta lambda plus omega naught squared equals to 0. So we have characteristic equation. All right, so lambda solutions lambda 1, 2 will be minus 2 beta plus minus square root of 4 beta squared minus 4 omega squared, right? So just a quadratic equation divided by 2. And now you see the reason why this factor of 2 was introduced, right? So it's a constant. You can introduce it anyway, in any way, just to make your life slightly more better, slightly more convenient. So factor of 2 was introduced so that these 2 and these 2 gets cancelled, and we will have just a beta in the solution, right? Decaying constant. Okay, so as a result, and also here we have 2 and 2 from here, right? So it will be minus beta plus minus square root of beta squared minus omega naught squared. So only with these lambdas, these can be a solution of this differential equation. Right? You know what? No, I cannot. I need to frame the right formula, right? I don't know why I framed that before class. I feel it's annoying. Okay. Cannot stand it. So as a result, of course, solution can be written. All right, so it will be general solution. Of course, e to the power of lambda 1t and e to the power of lambda 2t, those are particular solutions. Now we are writing general solutions, right? And you know how to construct a general solution of second-order differential equations. You find any two particular solutions, linearly independent, important, linearly independent, and then you construct linear combination of them, right? And that is solution. So, of course, it will be C1 e to the power of lambda 1t plus C2 e to the power of lambda 2t. And of course, now we can write explicitly. You know what I will write underneath? Right, so x as a function of time will be equal. E to the power of minus beta t I will factor out immediately. E to the power of minus beta t. And inside, we're going to have C1 e to the power of this. First, I think I wrote with, yeah, positive. Beta squared minus omega squared t. So lambda 1 and then plus C2 e to the power of lambda 2 minus beta squared minus omega naught squared, right? Yep. So that's the solution. Okay, let me frame it because we are going to address it from time to time. Okay, so let me check if I mention everything. Yep. Okay, so now, of course, different situations are possible depending on the sort of relations between beta and omega naught. Right. Because, yeah, if beta is less than omega naught, then this will be imaginary. If beta is larger, then this will be radical real. This radical will be real. So different situations are possible. So now we need to discuss all those possibilities, right? And, all right, so let me put, okay, I will just put a big new bullet, right? And label it weak damping, of course, right? Weak damping. So basically it happens when beta is, wait, here subscript 0 disappeared somehow, right? So when beta is less than omega naught, beta is less than omega naught, right? So weak damping. So as a result, of course, these are imaginary. So let's show that imaginary part explicitly. So I will write it beta squared minus omega naught squared. It's exactly the same in both, in this and that. T over here, T is missing. Right. Okay, now that this is solution. Right. So it will be, of course, I, and let me introduce new frequency omega 1, where omega 1 is basically this radical when we flip the order of these terms. Change the order. Omega naught squared minus beta squared, right? Okay, you see, now we're getting more omegas. Here we had omega sub 0. Now we're getting omega 1. Let me frame it because it's an important, and it's basically a frequency over system exposed to a damping force, right? So frequency of oscillations over system with damping. Right? So let me check if no, it's enough. Okay, so now let's rewrite the solution, right, using this omega 1. So it will be x as a function of time equals e to the power of minus beta t decaying exponential, right, and c1 e to the power of I omega 1, all right, t, and plus c2 e to the power of minus I omega 1 t. So it's one form, right? But disadvantage of this form that, yeah, these are, you remember the previous class, these are complex, and of course, as a result, these constants are also complex, right? So we can, of course, change it to a different form. But before I change it, let me write this, right? So this is decaying exponential, right? Oops. Decaying exponential. And of course, this is undamped oscillations, right? Undamped oscillations, but with a different frequency, with the frequency omega 1, which is smaller than frequency omega naught. So if you add damping, the system will still oscillate, but of course the frequency will be smaller. But of course the period, right, time distance between peaks, of course, is going to be larger, right? So this is which way I wrote undamped oscillations with lower frequency. Undamped oscillations with lower frequency. It's difficult to write here. Frequency omega 1. Okay, so now let me rewrite it in the form of, how we call it, a phase-shifted cosine solution. Every time I struggle remembering that term, phase-shifted cosine solution, right? So it will be different form x as a function of time. Okay, you know what? Too much of overlapping. Let me rewrite it. X as a function of time equals e to the power. You know what? No, let me first write a constant. Yeah. A. That A. E to the power of minus beta t. We know how to make a transition from this form of the solution to phase-shifted cosine solution, right? We've done it in the previous class. Right. Times cosine omega 1 t minus delta. So now instead of C1 and C2 constants of integration, we have A and delta constants of integration. Yeah, you remember that. So that's the form of the solution which is used quite often, right? More often even than this, right? So now then, of course, we can plot it, right? Let's just quickly plot it. Okay, I will do it here. So that's x. Again, what is x? It's a response of the system. It's a displacement of the system from the equilibrium, right? So we have undamped oscillations, right? But then we have a damping factor. So as a result, those undamped oscillations are sort of modulated, right? So let me first draw this modulation, something like this, right? And then our cosine function. So it's a cosine. Of course, it starts from the maximum. So it will be first this. And again, frequency is smaller than natural frequency, right? Again, these distances between peaks, right? Over here, it's tau. Between these two adjacent peaks, again, tau, and so on, right? What else needs to be mentioned? Yeah. Which parameter describes a decay rate? How fast system loses its amplitude? How fast it decays, right? So of course we can introduce time. We can introduce time, which is 1 over beta, which tells us stretch of time over which amplitude gets reduced by a factor of e, right? So amplitude gets to 37% of its maximum value, right? So we can introduce that also, maybe approximately here, let's say. So this t equals 1 over beta, and which way I label it? Let me draw it here, right? So here at that moment of time, amplitude, let's say this is amplitude, right? So over here, it's amplitude over E, right? And obviously, which parameter describes decay rate? It's beta, right? It's beta. And so in this case, so decay parameter is equal to the damping constant, right? So we're going to identify these decay parameters for each case, right? So for a weak damping case or under damping, decay parameter equals to a damping constant, it's beta, right? But for different cases, decay parameter will be different. Okay, so in this case, I can write some decay parameter equals to beta. Okay, so I will frame it because at the end, we will collect all these decay parameters, right, to see which system dumps energy the most efficiently. Right? So, okay, so let me check what else. Yeah, that's it. Right. So it should be enough. So in this case, system oscillating, but of course, amplitude is going down, and if you wait long enough, oscillations will disappear. Okay, so now next case, strong damping. So let's look at the strong damping, then critical damping, and then a few words about summary, and then driving oscillations. Okay, so let me put a new bullet, and this is strong damping. And of course, in a strong damping, beta is, of course, larger than omega naught, right? And of course, in this case, again, this is our solution, right? We're just adjusting this solution for this or that particular case, depending on the relationship between beta and omega naught. So these radicals are real. So now, these beta squared minus omega naught squared, this radical, radical is real. Right. So we cannot do anything about this, so we just rewrite it in a slightly different form. I will just combine this exponential term with that one, because it will be easier to get a decay parameter. I have to rewrite the solution. So it will be C1 e to the power of, first I will write which term? Okay, with minus, okay. Minus beta minus square root of beta squared minus omega naught squared, right? Times t. It's this times that, right? Yeah. And now the second term, C2, plus C2 e to the power of, again, I will take it outside here, minus beta plus square root of beta squared minus omega naught squared, t. Oi, t out. Bracket and then t. Right. Bracket and then t. Yeah. I used to analyze this, and I would look at some special conditions, right? Initial conditions, right? And then at some point, I decided not to do it anymore. So first, let's sort of identify the decay parameter first, and then I will just draw a couple of simple pictures. First of all, so which parameter describes a decay rate? So both of these decays, right? This and that, right? But which one decays faster? Obviously, this one here we have beta minus this radical. Here we have beta plus this radical. So this factor is larger. As a result, this term decays faster. So when this term is out, basically, right, this will still struggle being alive, right, staying alive. So this lives longer. As a result, these terms controls a decay rate. So this factor in front of t, right, that's our decay parameter. Again, here we have e to the power of minus beta t, so that factor beta in front of t, right? Controlled decay rate, and that was our decay parameter. But now this whole construction, which stays next to t, that's our decay parameter, right? So let me write something. So this decays faster, right? And this, of course, decays slower. And of course, leaves longer, controlling our decay rate. So as a result, I can write, so decay parameter is that. So decay parameter equals what? That's beta minus square root of beta squared minus omega naught squared. So that's our decay parameter. Let me frame it, because again, as I said, at the end we will combine them. Okay, let me just plot a couple of simple graphs, right? Again, as I said, a few years ago, I used to apply initial conditions, trying to get them, but then decided, no, it's not worth of trouble. So let me plot. What if we have, for example, these initial conditions? Initial conditions first. Let's assume that the system is at the equilibrium, and so initial position is 0, right? And then we kick it. So initial velocity is not 0. So that's our initial conditions, right? So if initial conditions x naught equals 0, and which way I wrote, v naught is not 0. So basically, we push the system out of the equilibrium at the initial moment of time. Of course, what will be the response of the system? Again, if I plot it, so x as a function of time and time. Of course, the system will first go away from the equilibrium, right? And then it will go back to the equilibrium pretty much, and it will take an infinite period of time, right? So it will behave like this, right? So something like this. So if you push the system from the equilibrium, so it will first reach the maximum displacement from the equilibrium, and then it will slowly just goes down to 0, right? It will go back to the equilibrium. So again, I just a few years ago, I applied these initial conditions and carefully applied them to the differential, to this x. But of course, it's kind of tedious. It's more like a algebra, right? Not worth of time. And another situation. So what if we have these initial conditions? What if we displace the system from the equilibrium? Initial velocity is 0, and then release it. Of course, in that case, it will just decays exponentially. Right, so if we plot versus t, and I didn't write initial conditions. So this will be x, and so initial conditions. What if x naught is, I said, displaced, right? So v naught will be 0, and x naught is not 0. All right, so in this case, decay, the behavior will be like this, right? So it will just, and will go to 0. So no oscillations, right? Because the medium is too viscous, right? So that's decay parameter is here, right? And now the last case, critical damping, when beta equals to omega naught. Right? Okay, I will probably try to put a few lines over here as well. So let me put a new bullet. So now critical damping. Critical damping. So in this case, beta equals to omega naught. I think I just used a frame, yeah. Right. This red marker is from different batch and it smells so strong. And of course now we are in troubles from the mathematical point of view, because in this case, what? Lambda 1, 2 is just a 1 lambda, right? So in this case, lambda 1, 2 equals to just 1, right? Minus beta. So we have only one solution of characteristic equation, and of course it means that we can construct only one particular solution, right? So as a result, only one particular solution, so which is x equals minus e to the power of minus beta t, right? And big set face, because we need two particular solutions in order to construct a general solution of the second order differential equation. All right, so what can be done in order to construct? Now we need to somehow construct the second particular solution, and very important, linearly independent, right? So you need to have two linearly independent particular solutions in order to construct the general solution, right? Okay, so what can be done? Again, I think once or twice I spent some time getting through the derivation, right? Using the method of variation of constants, right? In order to get the second linearly independent, of course, linearly independent with this second linearly independent particular solution, right? And then at some point I decided, no, it's not worth, because it's just pretty much like calculus, right? One of the methods of calculus. I will just post it on Blackboard. If you want, you can read it, right? But again, it's not that crucial, right? So after some time, I stopped deriving the second particular solution. So I will just write it down using the theory of differential equations, right? So we can, something like this, we can write the second particular solution. Again, linearly independent. So it will be just t times the same exponential factor. Right. Okay, so which way I wrote? Okay. Using, you know, it will be difficult to write it there. Or maybe using differential equations theory, right? We can write the second we can construct the second linearly independent particular solution. Linearly independent particular solution. Linearly independent solution. Let me abbreviate it, make it shorter. Second linearly independent solution. And that is x equals t times e to the power of minus beta times t. So that will be our second particular solution. Okay, let me frame it over here.
And that's only due to the fact that we have critical dampening.
It's only for critical
conditions?
damping, right? Because for the previous cases, we had the two lambdas, so we could construct two linearly independent particular solutions, right? And of course, theory of differential equations. If you have second order differential equation, and if you have two linearly independent solutions, construct linear combination, and that's the general solution of your differential equation, right? But in this case, we have only one, and so you just need to find any other linearly independent particular solution, right? And
Right.
yeah, there is a method, right? So as I said, method of variation of constants, right? And naturally, using that method, you can construct, and that will be the second one. Of course, it's not the only one. You can come up with something else, probably, right?
So that's calculus of variations?
Okay, you can see it's not calculus of variations. No. It's much simpler, right? So you assume the solution, right? So and then with the constant, and then you make that constant as a function of time, and then you that solution plug back into the differential equation, massage it, right? And then you will find that constant, which depends on time, right? So it's quite straightforward. No, it's not. It has nothing to do with calculus of variations. Nothing.
Okay, thank you.
It's barely physics. The derivation is just a pure calculus. So I decided to save some time. Okay, so now as a result, we can write a general solution, again, for the critical case. Okay, I hate erasing this, right? Let me think. I think I don't need that. That's why I like big boards when I teach classes like this, right? Yeah, I think I should be able to erase. When you can keep everything and you still have space to write. Okay, I will keep this general solution for now. Okay, so now general solution for the critical damping case. Which constant I use? I think still I use C1. Yeah, C1 and C2. C1 e to the power of minus beta t and plus C2 times t and e to the power of minus beta t. So that's our solution in this case. It's basically, again, still this solution, but adjusted for this special situation, right? And so again, no oscillations, right? No oscillations and, yeah, of course, right. No oscillations. I thought about putting some face, right, smiley face, but I don't know if it's a good or bad, just fact, right? No oscillations. Sometimes in some examples, some applications it's good, in some applications it's bad, right? So it's neither good nor bad. It's just a fact. So now, both of these decays, right? This decays, that decays. Of course, this decays somewhat faster maybe, right? But over here, there is a small battle, right? Okay, no, battle, it's too big word. There is an attempt to fight between this function t and this exponential factor, right? Exponential function. And of course, this battle is, okay, attempt to fight will be miserable because basically this decays so fast, so it will suppress this t badly. Of course, t is trying to grow, but this decays. It's basically like a battle between, I usually compare this fight with the fight between a lightweight boxer and a heavyweight champion. So of course, everyone knows what will be the outcome, right? Of course, this exponential factor suppressed it completely, right? So it will try to grow at the very beginning, but of course, it will go to 0 eventually, right? So pretty much at the same rate as that. So which parameter, or what can we say about the decay parameter? Because that's what we want to get for all of these cases. Decay parameter in this case is beta, right? Decay parameter is beta. Right? So that's the factor next to that in that exponential. So let me also write, so e to the power of minus beta, of course, eventually wins over t, right? Because again, I compare those with the fight of those two boxers, right? And so yeah, decay parameter. So let me write down the decay parameter. In this case, decay is beta. Again, let me frame it. And again, I was just before, I used to look at some special initial conditions. It's not a worth of that, right? It's just simple application of initial conditions for general solution. All right, so now let's collect all these decay parameters to one table and one plot in order to see, maybe we can see something useful. Right. Okay, so now all these red bullets over. So now let me put a blue and let's compare these decay parameters. All these decay parameters. First, I will create a table like in the book, right? Yeah, and we need to understand how do we look at this situation. So the system, the mass spring, right? And of course, in general, it can be more complicated than that. The system is given. So natural frequency is given, determined. So we're not changing that. So omega naught is there. And then we can expose that system, that mechanical system, oscillating system, to a different, exposed to different medium. Right? So first it can be in the air, so the small weak damping case. Then we can put it, in water. So beta will be larger, right? So it may be still weak damping or maybe over damping, who knows? And then you can put it in the oil, for example, so beta will be larger. You can expose them to something else, right? So we basically, what we're going to do, we assume that omega naught is given, system is determined, and then we'll just change beta, right? Change the damping constant. Basically, it's like exposing a system to a different medium. Right. So let me write. So we assume that omega naught is fixed. Basically, it means we don't change system. We don't change an oscillating system. Okay, our oscillating system. Right. We just change beta only, right? So now let me create the table first. So first, in the first column, it's a case, damping case, right? Weak damping, critical damping, over damping. No, first we will start with no damping, right? Then the second column will be what? Beta, damping constant. It's not decay parameter, damping constant, right? And the last column, it will be, decay parameter, which we identify. Decay parameter. Right. And of course, we will start with no damping, none It's a previous class material, right? No damping, of course, beta equals to 0. And decay parameter, of course, 0. Then, weak damping or weak underdamping. It's the same, weak damping or underdamping. Underdamping. Of course, beta is less than omega naught. Right. Again, omega naught is some like an intrinsic parameter of the system. And beta we change. Right? Beta basically like a variable. Right? Beta is less than omega naught. Underdamping and decay parameter, it's beta. So decay parameter equals to our variable, because you remember B now we treat as the variable, we just change medium. So, and decay parameter is beta. Now, next I think critical, right? Yeah. Critical damping. In the critical damping, of course, now our variable beta equals to omega naught. And in the critical damping, it's the last case. Again, decay parameter equals to the damping constant, beta. So it will be again beta. Okay, and then overdamping, right? Overdamping, of course, now beta is larger than omega naught. It will be clearer when we plot. It will be better even when we plot. And overdamping, where is our overdamping case? It's a strong damping. Strong damping, overdamping, it's this beta minus that radical. Beta minus square root of beta squared minus omega naught squared, right? So, okay, that's the table. And now let me erase this. Okay. Do I need it? No, it looks like I should be fine. So now let's plot. And I'm going to plot, as I said, this beta is our variable. So it will be our horizontal axis. And decay parameter will be vertical axis. So I will probably, let me step away slightly. So that's our decay parameter, vertical. And then horizontal is our beta. As I said, we keep system the same. As a result, this omega naught is fixed, given, and we just change medium and see what will be decay parameter. Actually, not see, we know already. Now we just I want to plot it, right? Because when you plot it, it looks better. So let's start with no damping. So beta equals to 0. Oh, so, okay, I will use red. So this is our first point. Beta equals 0, decay parameter is 0. 0, 0. Then underdamping. So beta, when our variable beta is less than omega naught. So we're talking about this case, right? So beta less than omega naught, so we're talking about this part of the curve. And what happens at that part of the curve? Decay parameter, that's our y-axis, right? Decay parameter equals to our variable. So basically, it's a straight line at 45 degrees. Y equals x, right? That's what we have here. But again, only for beta less than omega naught. Okay, so let me plot it. So let me this, and that's our straight line where beta decay parameter equals to, underdamping case, this case, right? Decay parameter equals to beta. So this is straight line. Then critical damping, when our variable beta is at omega naught. So we are here, right? And what we have over there, decay parameter equals to beta, right? It matches critical damping case, matches underdamping case, right? So it's just this point, critical damping. And then after that, when our variable beta is larger than omega naught, so we're talking about that part of the curve over here, right? Over here, decay parameter, this decay parameter equals to beta minus something which is smaller than beta. Right? So if you plot it, you will end up with something like this. So this is which way I wrote. So this is beta, and this is beta minus square root of beta squared minus omega naught squared. So now, what can we get out of this? Of course, sometimes decaying is bad, so you want to have some system oscillating. You want to oscillate the system. But sometimes you want, there are some applications where you want energy of an oscillating system as fast as possible, right? And of course, by looking at this curve, you can tell immediately which damping case you should use in order to damp energy in the most efficient way. Of course, you need to arrange your system to be critically damped, right? So basically, if you want to keep your system stable against some oscillations, it should be arranged using critical damping. Examples. Of course, you all work in the lab, right? Using equipment. You know old, for example, voltmeters with needles. Of course, can you imagine, for example, let's say that a needle is damped, oscillations of the needle is damped using underdamping case. You're trying to see the actual reading, and your needle will be oscillating, right, for a few minutes, right, reaching that equilibrium. If it was designed like this, that voltmeter will fly out of the window in no time, in my case, right? Because it will be really annoying. You want to see the results, and it keeps oscillating. Of course, you need to arrange it. You need to use critical damping so that the needle would be displaced maybe once from the actual reading, and then it will go to the actual reading as fast as possible. Right? Or if you, for example, use in a car suspension, right? After the bump, you don't want to oscillate for several minutes, right? With underdamping, you will feel sick, right? Of course, you need to arrange your car suspension. You need to arrange it in such a way so that energy will be damped as fast as possible. And of course, it happens when you use critical damping. Right? Then another example, again in the lab, right? For example, let's say you use spectrometer. Let's say, like in my case, let's say we measured the spectrum of a laser in a pulsed mode. And in that case, the spectrometer must be as stable as possible without any oscillations, without any experiencing any vibrations. In that case, optical table usually, we floated the optical table, right? So there are 4 pneumatic legs, right? And as a result, table like, like in the water, right? Again, the same critical damping is used, right? So if you displace it slightly, then it goes back to the equilibrium as fast as possible, right? So sometimes damping is bad, but sometimes damping is very good, right? And you need to damp some energy sometimes as fast as possible. But of course, you cannot dump energy out of the system faster than if you use critical case. That's the maximum. God created nature this way, right? Unless, of course, you decide to use some external force acting on the system. But of course, that will be a completely different situation, right? Okay, what else? Examples. You know what? I will probably just write the sentence in order to sort of summarize the meaning of this plot. So, if you want to keep something stable against oscillations, you need to arrange it to be critically damped. Let me write that sentence, right? So it would logically complete this. And then we'll move into different part. Okay, so let me just rewrite from my notes. If you want to keep something, okay, to keep your system, to keep, okay, let me write something. STH something, I abbreviate it quite often, something against oscillations. Right, you need to arrange it to be critically damped. You need to arrange it to be critically damped. Right. At least sometimes critical damping is useful. Right. And of course, yeah, you can apply any initial conditions for any of these cases, right? As I said at the very beginning, I used to do it, and then any of you can easily apply initial conditions, right? So as a result, I decided to skip it, right? Okay, so next level of, okay, so we're basically slowly, step by step, trying to make our system more and more complicated. So we passed a no damping case, then we added damping, right? We analyzed all possible damping situations, and now, of course, let's try to drive a system. So let's add a driving force to the system. Again, still, damping is still there. Damping force is still acts on the system. But now we're going to add a driving force. I guess I will start erasing that part, right? Okay, I think. Okay. Yeah, I think I don't need this. Yeah. And again, remember, so when you expose the system to damping force, frequency is going down. Of course, period becomes longer, right, larger, and the frequency is going down. So we have, as a result, we have two frequencies. Omega naught natural frequency, if the system is not exposed to any damping forces, and then omega 1, if the system is exposed to a damping force. So now driven damped oscillations. Driven damped oscillations. So what in terms of time? 15. Okay, so we will be able to probably write down the equation and solve it. Okay, so now let's assume that a system is exposed to some driving force. So now we have three forces: restoring, damping, and driving force. So now we have F restoring, F damping, and this one, which way I label it? Just F. You know what? No, I don't like it. It's FR restoring, of course, it's a minus KX. Then damping force FD equals minus BV. All right. And now we're going to add F as a function of time now. A driving force. Okay, so now I'm not going to redraw that picture. I will just write down the differential equation immediately, right? So now okay, let me write first in the form of the Newton's second law, mx double dot. I'll keep it on this side. No, immediately move to this side. Okay, it doesn't matter. So minus bx dot minus kx and plus force, driving force. And again, divided by m. After dividing it by m, we will end up, of course, with x double dot plus b over m x dot plus k over mx, and I will keep f on that side. And again, who wants to drag this constant? So exactly the same substitutions, right? So this is our 2 beta. Again, this is our natural frequency. And now instead of f over m, f over m, let's label it as f small. And you need to remember that now this has units of acceleration, right? It's no longer, it doesn't have any longer units of force, right? So this is force, but once you divide it by mass, so it will have units of acceleration, right? And again, no restrictions on time dependence. So right now, it's just completely general situation, right? In a second, of course, we will impose some special form of time dependence. Okay, so let me rewrite this final differential equation. Of course, then we will start insulting it, giving it names, calling it names. So x dot plus omega naught squared x equals to f as a function of time. So that's our now differential equation. So again, second order. Linear and what is the major difference relative to the differential equations which we had before? That now we have a free term. We have a term which doesn't have these x agents, right? So now we have a free term. It means that now it's a inhomogeneous differential equation. So that's the major difference between this equation and the previous one. So second order inhomogeneous. Right, and again, inhomogeneity is in here, right? So and of course, now we need to recall. So how let me just check if I mentioned, yeah, that's done. All right, so now let's recall, again, theory of differential equations. How can we solve inhomogeneous differential equation? I'm sure that some of you remember, right? We need first solve, find or solve, right? Find a general solution of homogeneous differential equation. Just basically dump this part and solve, just write a general solution of homogeneous differential equation, right? And then find any particular solution of inhomogeneous differential equation. Not general, any particular, any solution, right? And then you have a general solution of homogeneous equation, any particular solution of inhomogeneous, and if you add these two solutions up, that will be the solution, general solution of the inhomogeneous differential equation. Okay, let me write it down.
What about Laplace in this case?
Okay, there are tons of different methods of using solving differential equation. Of course, you can probably use even Laplace equations. I mean, Laplace methods. Right? I haven't used it for quite some time. But here, Laplace method is not the only one. Right. So let me write. Probably I will do it like this. So general solution of inhomogeneous differential equation equals to, right? So general solution of homogeneous n plus any particular solution of this inhomogeneous differential equation, of the inhomogeneous differential equation, right? Right, so we can write, which way I labeled the general? Oh, okay, just x without anything. So x equals x with subscript h. It's a general solution of homogeneous differential equation, right? This one. N plus, sorry, which way I label it? X, just xp, yeah. Plus xp. Any particular. Again, you can find a gazillion number of particular solutions, right? You just need to find any of those. You can, I know, sleep on that. You can imagine that particular solution. You can, I know, pray for that, go to the church, right? It doesn't matter how, as long as you can find any particular solution which would satisfy the inhomogeneous differential equation. Okay, so and good news, we already know the solution, general solution of homogeneous equation, right? That's what we've been doing this class, right? We were solving this equation when it is equal to 0. So we know this, right? So we already know that. All right, so as a result, we just need to find this. To find xp somehow, right? So what in terms of time? Okay, so we still have 7 minutes. Awesome. All right, so let me write, since again, as I said, we know the solution of this, so let me write in terms of those lambdas. Right? So x as a function of time, it will be c1. I think I used that exponential form. Yeah. E to the power of lambda 1t plus c2 e to the power of lambda 2t and plus any particular solution, right? So what can be done in order to find particular solution? And that question, of course, is stated too early, because right now we did not specify what's the shape of the driving force, or what's the time dependence of our driving force. So first you need to say which force you apply, right? Explicitly, what is x, not x, f, or this f, right? And only then you can start searching for a particular solution. So let's assume the most pleasant case, and actually quite ubiquitous, right? So let's look at the case when f varies harmonically with time. And I think I use cosine function. Let me check. Yeah, cosine function. So let's assume that f is proportional to cosine omega t. So now different omega appears. Frequency of the driving force. Right. So as I told you, now we're going to have plenty of different omegas. And so now we assume that force, and again, we just need, for that force, we need to find any particular solution. Here are my markers. So let's assume that f as a function of time equals, I think I use constant a. No, f naught. F naught times cosine omega t. So now again, this omega, it's a frequency of the driving force. these cell phones, with the noises, right? Okay, so now we have omega naught. It's a natural frequency of the system. Omega 1, it's a frequency of the system which is exposed to some damping force. And now this is frequency of the driving force. And also, another thing, guys, now this system, is this system an isolated system? Now the system is no longer isolated, right? Because now we have a driving force. It's sort of like an influence from the outside world, right? So now energy can be, not can be, energy is dumped into the system, or can be taken out, right? Okay, so now we can write our differential equation. Right. And again, so we need to find, let me emphasize, so we need xp. That's the goal now. So let me rewrite this differential equation explicitly with that function. So plus 2 beta x dot plus omega naught squared x equals to f naught cosine omega t. Again, any particular solution, right, needs to be found. Yeah, I will summarize these frequencies later, right? So how can we solve it? Cosine omega t function, it's bad to complain, right? Cosine sine functions are nice enough. But if we can make it even nicer, why not, right? So, but in order to make it look better, right, and to solve this differential equation, so let's go to the complex world, right? Let's lose touch with reality and go to the complex world, right? Let's go to the complex world. Right. So let's write down another differential equation, right? But now for y. Y double dot plus 2 beta y dot plus omega naught squared y equals to f naught sine omega t. And of course you understand, who cares that I'm creating this second differential equation, and I'm going to add it to the first one after multiplying by I, right, in order to create z functions, right? Because, yeah, it will make our life somewhat easier when we go to that world, right? And of course, this equation and that equation, basically, they don't interact inside of that complex world. So once you solve that complex equation in the complex world, you take your solution, right, separate real part and imaginary part, and we will get our solution, right? So let's do it. So of course, we can introduce z. It will be x plus I y. And as a result, we can introduce this differential equation in the complex form. Right? So it will be z double dot plus 2 beta z dot plus omega naught squared z and equals f naught e to the power of I omega t. Yeah, in this form, yeah. Okay, let me frame it, because now we're going to dance around this equation all the time, right? Oh, it's okay. So let's stop at this point, right? Basically, now we just we need to find any particular solution. So we can say I want to search for particular solution in this form, and we can try it, right? And of course, in this case, it's obvious which form we're going to try, right? So since we have exponential factor over here, right? It's in that free term, it makes sense to search for a solution in the exponential form. It will be the most convenient, right? And again, we just need to find any, right? Of course, it's easier to find. It's better to find the easiest possible form, the easiest form, right? And then, of course, we will just need to find the factor in front of that e to the power of I omega t. And then another maybe 5-10 minutes, and we will be able to write the general solution. No, particular solution, and only then a general solution of the inhomogeneous differential equation. Right. So it feels like next class, maybe I will be able to finish this chapter 5, right? Or maybe if maybe 5-10 minutes I can spend. No, in a week on Tuesday we're going to have a midterm exam, most likely, right? Okay, and after this, so on Thursday definitely we will start discussing a calculus of variations. You just mentioned it today, right? Calculus of variations, right? Basically as a preparation for the calculus, for the Lagrangian formalism, Okay, guys, so that's it for today.